Hello, and welcome to Bedtime Science. Whether you're winding down for the night or simply looking for a calming exploration of the universe, you're in the right place. If you enjoy delving into the mysteries of space, the natural world, and the forces that shape our daily lives, don't forget to like and subscribe. And of course, let us know where you're watching or listening from. It's always fascinating to see how the tides affect different parts of the world, and your location might just give you a unique perspective on today's topic. Tonight, we're going to explore one of the most captivating and calming phenomena on Earth, the tides. The gentle rise and fall of the oceans have fascinated people for centuries, but have you ever wondered what's really behind these rhythmic movements? Could something as distant as the moon really have such a powerful effect on our planet? In the next few moments, we'll be diving into the science behind how the moon controls the tides, and what that means not just for our oceans, but for life here on Earth. So, get comfortable. Relax, and let's begin this journey into the cosmic dance between the Earth, the Moon, and the Sun. Tides are one of nature's most mesmerizing rhythms, an eternal dance of the oceans that has captivated humans for millennia. The ebb and flow of water along coastlines may seem like a simple, everyday event, but they are in fact a powerful reminder of the cosmic forces that govern our planet. Tides, influenced by the Moon and the Sun, are universal, affecting not just Earth, but also many moons, planets, and even distant celestial bodies in our solar system. This rhythmic movement of water is more than a local occurrence. It's a phenomenon that transcends the boundaries of our planet and links Earth to the greater cosmos. Long before scientists understood the mechanics behind tides, people noticed the recurring rise and fall of the ocean waters. Ancient cultures were among the first to observe and mark these patterns, using them for navigation and understanding the passage of time. The earliest documented thoughts on tides come from the ancient Greeks, notably from thinkers like Aristotle and his student Theophrastus. Aristotle, in particular, believed that tides were connected to the movement of the moon, though he was puzzled by their exact cause. It wasn't until later, during the Age of Enlightenment, that we would come to understand the science behind these rhythms in more detail. The Greeks were not the only ones to wonder about the tides. Many ancient civilizations, from the Babylonians to the Polynesians, saw the tides as a reflection of the universe's deeper mysteries. They observed how the moon seemed to control the sea, rising and falling like the heartbeat of the earth itself. But it was not until much later, in the 16th and 17th centuries, that the scientific community began to tackle the true nature of tidal forces. One of the pivotal moments in understanding tides came with the work of Sir Isaac Newton in the late 1700s. Newton's groundbreaking theory of gravity suggested that the moon's gravitational pull on Earth caused the oceans to bulge out towards the moon. This was the first time anyone had been able to explain the cause of tides with any scientific rigor. But Newton wasn't the only thinker whose ideas helped shape our understanding of tides. Philosophers like Georg Wilhelm Friedrich Hegel, often overlooked in the context of physical science, pondered the cyclical nature of life and the universe. His musings about patterns in nature, while not directly related to tides, echoed the same universal principles we now see governing the rise and fall of the oceans. Hegel believed that the universe was in constant flux, with everything following cycles of expansion and contraction. These ideas, although philosophical, offer an interesting lens through which we can look at the behavior of tides, which, much like the ebb and flow of energy in Hegel's theories, are part of a broader, never-ending cycle that ties together the moon, the Earth, and the Sun. In fact, when we observe the regularity of tides, it's easy to see how they are a reflection of the rhythm that governs much of the universe, a cosmic pulse. As we move beyond philosophical musings, we can look at the practical significance of tides. Tides play a crucial role in Earth's ecosystems. The constant motion of ocean waters helps regulate the climate, support marine life, and even influence weather patterns. Without tides, many marine organisms such as clams, seabirds, and crabs would find it difficult to survive. The rise and fall of the water levels create rich habitats in the intertidal zones where life thrives. In a way, the tides are not just a scientific curiosity, but an essential part of maintaining the delicate balance of life on Earth. But tides are not just important for marine life, they are crucial for human activities as well. For centuries, fishermen have used tidal patterns to determine the best times to fish, and coastal communities have relied on them for navigation. Even today, tides are essential for managing ports and harbours, as they dictate when ships can safely enter and leave. In many ways, the rise and fall of the oceans have shaped human history, from ancient trade routes to modern shipping lanes. Understanding the tides is also crucial for environmental science. The study of tidal forces helps us understand how climate change is impacting sea levels, and how rising ocean temperatures might affect tidal behavior in the future. As the Moon continues to drift farther from Earth, it will cause tides to gradually diminish, affecting both the Earth's rotation and the environment. These changes, although occurring over long periods, remind us that the tides are not just a part of the natural world, they are a living record of our planet's dynamic history. Tides, in their quiet rhythm, are a constant reminder that we are deeply connected to the forces of nature. They are both a daily phenomenon and a cosmic event, influenced by the distant Moon and the Sun. The ebb and flow of water along our shores serve as a reminder of the vast interconnected systems that make up the universe. As we continue to study the tides, we uncover not only the story of our own planet but also the fundamental principles that govern the cosmos itself. Isaac Newton's law of gravity is often one of the first scientific principles we learn about when we study the natural world. It's a simple yet powerful idea. Every object in the universe exerts a gravitational force on every other object. The strength of that force depends on the masses of the objects and the distance between them. This is the very principle that explains how the Moon, though millions of miles away, can pull on Earth's oceans and create the tides. Newton's discovery in the late 1700s laid the foundation for our understanding of gravity, and it's a key reason we can explain the mechanics behind the rising and falling of the sea. However, Newton wasn't the only person to shape our understanding of gravity. While his law of universal gravitation was revolutionary, it didn't address all the intricacies of how gravity works in certain contexts, especially when it comes to something as complex as tides. That's where another important figure, Pierre-Simon Laplace, enters the scene. Laplace was a French mathematician and astronomer whose work in the late 1800s helped refine our understanding of gravitational interactions. He developed a more detailed explanation of how the Moon's gravitational pull affects Earth, taking into account not just the static forces, but also how the Earth and the Moon are constantly moving and interacting. Laplace's work was groundbreaking because it helped clarify the complex dynamic nature of the gravitational forces between Earth and the Moon. He took into account the varying distances between the two bodies as they orbit one another, which is essential to understanding the variations in the intensity of the tides. Without Laplace's contributions, our models of tidal behavior would have been much less precise. It's easy to take for granted how predictable tides are today, but Laplace's research was essential in making that possible. Another key figure in the study of gravity and its effects on Earth was Carl Friedrich Gauss, a German mathematician who made profound contributions to the fields of physics and geodesy. Gauss's work in the early 1800s helped scientists understand how gravity interacts with the shape of Earth, or more precisely, how the Earth's irregular shape influences gravitational forces. His work showed that gravity doesn't just act uniformly across a perfect sphere. Earth's surface is uneven, and this causes variations in gravitational strength across the planet. While this may seem like a small detail, it has huge implications for tidal dynamics. Gravity is not a one-size-fits-all force. It's influenced by the masses of objects, yes, but also by the way those masses are distributed. Gauss's contributions helped scientists account for the local differences in gravitational force that affect the tides differently in various parts of the world. But gravity, as we know, isn't the only force at play. In recent years, physicists have begun to explore theories that go beyond Newton's law to explain gravity and its effects on the universe. One such theory is that of David Bohm, a British physicist whose work in the mid-20th century offered a new perspective on the forces that govern our world. Bohm proposed a concept known as implicate order, which suggests that the universe operates as an interconnected whole, and that everything, from the smallest particles to the largest galaxies, is deeply entangled in a way that classical physics can't fully explain. In the context of tides, Bohm's theory suggests that the gravitational interaction between Earth and the Moon could be part of a much larger, more intricate network of forces. Instead of viewing gravity as an isolated force, Bohm's implicate order invites us to consider the possibility that the tides may not just be the result of a straightforward gravitational pull, but a manifestation of deeper hidden connections within the universe. The tides, in this view, would be just one of the many expressions of an underlying interconnected reality. This doesn't negate the basic principles of gravity, but suggests that there could be something more profound happening beneath the surface. Of course, not all scientists agree with Bohm's ideas. For instance, some argue that the traditional understanding of gravity, based on Newton's and Einstein's theories, remains the best explanation for tidal forces. Yet it's important to acknowledge that the world of physics is full of diverse and sometimes conflicting theories. This brings us to another interesting approach: modified Newtonian dynamics, or MOND, a theory that challenges the standard model of gravity. MOND, developed by Israeli physicist Mordechai Milgram in the 1980s, suggests that gravity behaves differently than Newton predicted, especially at large distances or in low acceleration environments, such as near the outer edges of galaxies. While MOND was initially proposed to explain certain anomalies in galaxy rotation curves, it's an intriguing concept to consider when we think about the forces at play between Earth and the Moon. Could the gravitational forces governing tides, which involve long-distance interactions, behave in ways we don't fully understand yet? MOND invites us to entertain the idea that gravity might not work exactly as we've always believed, potentially reshaping how we think about not only tides, but also the forces that shape the universe. While we typically think of gravity as a force that acts on large objects like planets and moons, its effects extend all the way down to the molecular level. When you think about the tides, you might picture the oceans rising and falling in massive waves, but gravity's influence also extends to water molecules themselves. This is where the work of Niels Bohr, one of the pioneers of quantum mechanics, becomes relevant. Bohr's theories helped us understand the behavior of atoms and molecules, and while his work wasn't focused on tides, it's useful for imagining how even the smallest particles in the water respond to gravitational forces. In the same way that Bohr's theories explain the behavior of electrons within atoms, we can begin to think about how the Moon's gravitational pull affects the water molecules in the oceans. The force might be too small to directly observe at the molecular level, but over vast stretches of water, these tiny effects accumulate, resulting in the larger tidal movements we see on the surface. Understanding how gravity works at the atomic and molecular levels could one day offer new insights into how gravity influences not just the oceans, but every facet of our physical world. Gravity is more than just a force that pulls objects toward one another. It's a fundamental part of the fabric of our universe, shaping the tides, our planet, and even the behavior of the smallest particles. From Newton to Laplace to Bohm and beyond, the study of gravity is an ongoing journey, one that continues to reveal the deep hidden forces that govern not just our world, but the entire cosmos. The tides are a reflection of these powerful unseen forces, and understanding them brings us closer to understanding the mysteries of the universe itself. The Earth, the Moon, and the Sun form a dynamic trio, a delicate dance that has been taking place for billions of years. The relationship between these three celestial bodies is interdependent, each one influencing the others in ways that extend far beyond the simple motion of the oceans. This cosmic harmony, as explored by physicist Fritjof Capra, is a perfect example of the interconnectedness that runs through the entire universe. Capra's ideas suggest that everything in the cosmos is deeply intertwined, and the Earth-Moon-Sun system is a clear example of how even distant forces can have a profound impact on one another. The gravitational pull of the Moon shapes the tides, but it is the position of both the Earth and the Sun that determines how those tides ebb and flow in the rhythmic cycles we observe every day. As these three bodies move through space, their positions relative to each other create a complex and ever-changing pattern of forces. The Moon's gravitational pull is the most significant factor in tidal movements, but the Sun's gravitational influence plays a role as well. When the Sun, Earth and Moon are aligned, such as during a full moon or a new moon, gravitational forces combine, leading to spring tides, when the ocean's rise and fall are especially pronounced. These alignments create a gravitational amplification, a deep resonance that reflects the powerful interaction between these three bodies. To understand this interconnectedness on a deeper level, we can draw upon the work of Louis de Broglie, a physicist who proposed the wave-particle duality theory. De Broglie's ideas suggest that not only do particles like electrons behave both as particles and as waves, but perhaps celestial bodies like the Moon and Earth could also have a kind of quantum relationship. While this is a bit outside traditional views of gravity, the idea of quantum entanglement suggests that even vast distances between celestial bodies might not prevent some form of interconnectedness. Could it be that the Earth and the Moon are not only bound by gravity, but also through deeper, quantum-like connections that influence their behavior? The thought that these celestial bodies might be entangled in a way that is more complex than simple gravitational attraction is an exciting idea, though still speculative. But we don't need to dive too far into quantum theory to appreciate the harmonic patterns of the Earth, Moon, and Sun. The concept of harmonic resonance, as explained by physicist Hermann von Helmholtz, offers an interesting perspective on how these bodies might be in tune with one another. Helmholtz's theory of natural resonance suggests that certain systems, when placed in motion, vibrate at characteristic frequencies, and these frequencies can reinforce or cancel each other out. In the case of the Earth-Moon-Sun system, the positions of the Moon and the Sun create a sort of cosmic resonance, with the Moon's gravitational pull amplifying the motion of Earth's oceans in a steady rhythm. This resonance is part of a larger cosmic symphony, where even tiny changes in the positions of these bodies can create noticeable effects on Earth's tides. Looking beyond the immediate influences of Earth, Moon, and Sun, we must also consider the long-term effects of their interactions. The work of Gerard K. T. Hooft, a Nobel laureate in physics, has helped deepen our understanding of the fundamental nature of space and time. In his studies of fundamental physics, Hooft has shown that at the most basic level everything in the universe is connected through deep underlying principles. This could extend to tidal forces as well. Over the course of millions of years, the interactions between the Earth, Moon, and Sun influence not just the tides, but the very structure of Earth's orbit, rotation, and even the gradual slowing of the planet's spin. The Moon, for instance, is slowly drifting away from Earth, and as it does, the tides are gradually weakening. This long-term cosmic scale interaction is a reminder of the incredible forces at play in shaping the very nature of our planet's movement through space. As we think about the grand scale of tidal interactions, we can also consider the idea of cosmic synchronicity. This concept, explored by astronomer G. I. Tamman, suggests that the movements of celestial bodies are not random, but instead follow patterns that reflect a deeper underlying order. Tamman's historical studies of celestial alignments reveal that the positions of stars, planets, and moons are often in harmony, creating an intricate system of gravitational influences that ripple across the universe. The Moon's influence on Earth is part of this greater cosmic synchronization, where the positions and movements of bodies in our solar system follow precise patterns that have been occurring for billions of years. What's particularly fascinating is how these celestial alignments and movements influence not only our tides, but also other phenomena in the cosmos. For example, the gravitational effects between Earth and the Moon have a profound impact on the Earth's axial tilt, which in turn affects the planet's seasons. The Moon helps stabilize Earth's tilt, preventing drastic shifts that could create a more chaotic climate. This delicate balance between the Earth, Moon, and Sun is a key factor in the stability of life on Earth. The Moon, despite its distance from us, plays a pivotal role in maintaining the conditions necessary for life as we know it. The Earth-Moon-Sun system is not just an isolated phenomenon, it is a reflection of the greater order of the universe. The interconnectedness of these three bodies creates a harmonious relationship that shapes life on Earth in ways we are still uncovering. As we continue to explore the forces that govern our planet, we begin to realize that the tides are not just a surface-level phenomenon, but a manifestation of deep cosmic forces at work. The movements of the Earth, Moon, and Sun are not just about water rising and falling, they are about the rhythms that govern the very fabric of our universe. The rise and fall of the tides are much more than a simple push and pull between Earth and the Moon. In fact, the physics behind high and low tides is an intricate dance of forces, many of which we can trace back to basic principles like centrifugal and centripetal forces. These forces are at the heart of how tidal bulges form on Earth's oceans. The Moon's gravitational pull causes the ocean's water to move towards it, creating a bulge, but there's another effect at play too. As Earth rotates, the centrifugal force caused by this rotation creates a second bulge on the opposite side of the planet. These two bulges are what we observe as high tides. The spaces between them, where the water level is lower, are the low tides. It's easy to think of the process as simple. Gravity pulls the water towards the Moon, and Earth's rotation pushes it away. But the reality is more complex, especially when you start considering the delicate interactions between centrifugal forces, gravity, and the Earth's own movement. These forces are constantly shifting as the Earth rotates, the Moon orbits, and the Sun's gravitational influence also comes into play. Each of these forces has its own rhythm, and they work together to create the tidal cycle that we see each day. Yet, there's an intriguing complexity in how tiny changes can lead to big shifts in tidal behavior. This is where the field of chaos theory, first developed by Edward Lorenz in the 1960s, comes in. Lorenz's work on chaotic systems revealed that even small changes in the starting conditions of a system could lead to drastically different outcomes. In terms of tides, this means that even a tiny variation in the moon's position, just a fraction of a degree, could lead to noticeable changes in the tides we observe. The movement of the moon, in relation to both Earth and the Sun, is sensitive to small variations, and these differences can cause tidal patterns to shift in unpredictable ways. This sensitivity to small changes is a hallmark of chaotic systems. Chaos theory shows us that while the forces driving tides are constant, the way they interact can lead to outcomes that are not always easy to predict. So, even though we can generally anticipate when the tides will rise and fall, the exact height of those tides can be influenced by subtle factors that are hard to pinpoint, such as the moon's position in its elliptical orbit or the exact tilt of Earth's axis at any given moment. This idea challenges the simple, mechanical view of tides as a predictable cycle, and opens the door to more nuanced understanding. Taking the discussion a step further, the physics of tides doesn't just stop at the macroscopic scale. When you think about the forces at play, it's easy to forget that even the smallest particles, like water molecules, are also affected. This is where Lise Meitner's groundbreaking work in nuclear physics comes into play. While Meitner is best known for her contributions to the discovery of nuclear fission, her work also sheds light on how forces, including gravity, can interact at much smaller scales. Gravity, as we experience it, acts on large objects like planets and moons, but it also affects molecules and atoms in subtle ways. If we imagine the interactions between the moon's gravity and the water molecules on Earth's surface, we begin to appreciate that even the very structure of water itself is influenced by these celestial forces. On a quantum level, these interactions could even extend into the realm of quantum mechanics. Niels Bohr's work on the structure of atoms and the behavior of subatomic particles reminds us that gravity is not just a force acting on large bodies, but also one that could, theoretically, have effects on the microscopic particles that make up those bodies. This opens up the fascinating possibility that tidal forces, even though they manifest in large-scale ocean movements, might have a deeper quantum connection. Perhaps the gravitational pull of the moon is subtly influencing the behavior of water molecules on a quantum level, something that classical physics doesn't fully explain but could still be part of the intricate system of forces shaping the tides. As we look at the overall behavior of tides, it's clear that they don't simply follow a straightforward, predictable pattern. Instead, they're influenced by a variety of complex forces, some of which we can explain using classical mechanics, and others that challenge us to think beyond traditional physics. Mitchell Feigenbaum, a mathematician and physicist known for his work on chaos theory, explored how certain natural systems, like tides, can behave in a nonlinear way. In a nonlinear system, small changes can cause disproportionately large effects, leading to complex, often unpredictable behavior. The tides, as a system influenced by a myriad of forces, can sometimes seem to follow a set pattern, but they are also part of a dynamic system in which even the slightest changes in conditions could lead to notable shifts. This nonlinearity makes the study of tides a fascinating endeavour, as it challenges our assumptions about predictability. The forces governing tidal movements are not only influenced by gravitational pull, but also by the seemingly random variations that happen in nature, whether it's the moon's slightly altered position or the subtle changes in the Earth's spin. These unpredictable shifts are part of a larger chaotic system that gives tides their complexity, and why, although we can predict their general timing, their exact behavior may always have an element of uncertainty. So, the tides we see are the result of an intricate web of forces, centrifugal and centripetal, gravitational and chaotic, quantum and classical, that work together in a cosmic symphony. They remind us that even the most familiar phenomena, like the rise and fall of the ocean, are part of a larger, interconnected universe full of hidden complexities. Understanding the physics behind tides isn't just about knowing when the water will be high or low. It's about recognizing the deep, unseen forces that make these movements possible, forces that stretch from the quantum world all the way to the far reaches of space. The tides of Earth are not random occurrences, but part of a regular, predictable cycle that repeats itself day after day. The cyclical nature of tides is a fundamental characteristic of the oceans, shaped by the gravitational forces of the Moon and the Sun, as well as Earth's rotation. Understanding this regular rhythm is crucial not only for navigating the seas, but also for understanding the deeper forces at play in the natural world. Tidal cycles follow a clear pattern, occurring about every 12 hours and 25 minutes, which is the time it takes for a given point on Earth to return to the same tidal phase. This regularity allows us to predict when high and low tides will occur, and for centuries, it has helped fishermen, sailors, and coastal communities plan their activities. However, the rhythm of the tides is not simply a mechanical process. It is part of a much larger, interconnected system that follows complex laws of physics. The work of Henri Poincaré, a French mathematician and physicist in the late 1800s, provides us with a deeper understanding of the tidal cycle's predictability. Poincaré is best known for his work in celestial mechanics, particularly his studies of the orbits of planets and the Moon. He recognized that even seemingly simple celestial systems, like the Earth-Moon-Sun system, could display incredibly complex behavior when observed over long periods. His insights into nonlinear dynamics showed that while the tidal cycle itself is periodic, it is also influenced by small changes in the positions of celestial bodies, leading to slight variations in the tidal patterns we observe. While the tidal cycle might appear to be a simple, periodic event, Poincaré's work suggests that it is part of a much broader framework where even tiny variations can cause larger, more dramatic shifts. This notion of complex yet periodic systems can be connected to the work of Julian Barbour, a British physicist known for his theories on timeless physics. Barbour proposed that time itself may not be as we typically think of it, that the flow of time might be an illusion. Instead, he argued that everything exists in a series of nows, and the idea of past, present, and future is more a reflection of our perception of change than an objective reality. Barbour's ideas could have interesting implications for tidal cycles. If we view the tidal cycle as part of an eternal rhythm, not bound by the limitations of time as we understand it, then tides could represent a deeper universal pattern that reflects a cosmic, unchanging order. The Moon's influence on Earth's tides in this sense might not just be a physical occurrence, but could be seen as a reflection of deeper, timeless laws of nature woven into the fabric of the universe. As we continue to explore the complexities of tidal behavior, we can expand our understanding by looking at the tidal cycle through the lens of nonlinear dynamics and chaos theory. The work of Mitchell Feigenbaum, a mathematician known for his discoveries in chaos theory, provides valuable insight here. Feigenbaum showed that certain systems in nature, like fluid dynamics or the motion of objects under gravity, can exhibit chaotic behavior where tiny changes in conditions can lead to wildly different outcomes. In the case of tides, this means that while the general pattern remains stable, small shifts in variables like the Moon's orbit or Earth's tilt could have larger effects over time. Chaos theory reminds us that even systems that appear predictable, like the tidal cycle, can be influenced by an inherent level of unpredictability. For example, the gravitational forces that drive the tides are never static. They are constantly changing due to the Moon's elliptical orbit and the shifting positions of Earth and the Sun. These variations might lead to subtle changes in the timing or intensity of the tides, adding a layer of complexity to what might otherwise seem like a simple repeating cycle. While this doesn't make the tides unpredictable, it highlights the underlying complexity in the system that governs their behavior. At the most fundamental level, tidal cycles can also be examined through the lens of thermodynamics, the branch of physics that deals with energy flow and entropy. Rudolf Clausius, one of the pioneers of thermodynamics in the 19th century, explored how energy moves through systems and how the process of energy exchange tends to increase disorder, or entropy, over time. Tides, too, are influenced by the movement of energy. As the Moon's gravity pulls on the oceans, it creates potential energy in the form of tidal bulges, which are then transformed into kinetic energy as the water moves. This constant exchange of energy between the gravitational forces of the Moon, the motion of Earth, and the movement of ocean water is not only responsible for the rise and fall of the tides, but also for their stability. The gradual loss of energy in the Earth-Moon system caused by tidal friction is one of the reasons the length of Earth's day is gradually increasing over time. This process, however, occurs so slowly that its effects are imperceptible in our lifetimes, but are significant over geological timescales. In this sense, the tidal cycle isn't just a simple back and forth of water. It is a complex interplay of forces driven by gravity and governed by the laws of thermodynamics and nonlinear dynamics. It's a system in which energy is constantly exchanged, transferred and transformed, reflecting the broader rhythms of nature. The periodicity of the tides is not just a result of a straightforward, mechanical process, but an intricate dance between the forces of the cosmos. From Poincaré's insights into celestial mechanics to Barber's timeless physics, and from Feigenbaum's chaos theory to Clausius's work on energy flow, the tidal cycle is a profound reminder of the underlying complexity of the universe. Tides, in their rhythmic pattern, represent both the predictability and the hidden unpredictability of nature, a system in which even the smallest forces and shifts can have lasting effects. As we look at the tides, we're not just witnessing a natural phenomenon, we're observing the deep interconnected processes that govern the very fabric of the cosmos itself. Tidal friction is a slow but powerful process that affects both the Earth and the Moon. At the most basic level, tidal friction occurs because of the gravitational interactions between the Earth and the Moon. As the Moon's gravity pulls on Earth's oceans, it creates tidal bulges that move around the planet. However, because Earth is rotating, these bulges do not sit exactly beneath the Moon, but are slightly displaced due to Earth's motion. This displacement causes friction between the ocean's water and the solid Earth, which slows down the rotation of the planet. This frictional force gradually saps the Earth's rotational energy, causing Earth's day to lengthen, albeit by just a fraction of a second per century. While this effect might seem small on a human timescale, over millions and billions of years, the impact becomes significant. As Earth's rotation slows, the Moon is gradually moving away from the planet at a rate of approximately 4 centimeters per year. It's an incredibly slow process, but one that has profound long-term implications. In fact, the Moon is currently about 39,000 kilometers farther away from Earth than it was when the process began. This drift away from Earth is a direct result of the tidal friction caused by the interaction between Earth's rotation and the gravitational pull of the Moon. To understand the broader implications of tidal friction, we can draw an interesting parallel with galactic dynamics, thanks to the work of Geoffrey Burbidge, a renowned cosmologist. Burbidge's research on the formation and behavior of galaxies revealed that, much like the Earth-Moon system, galaxies also undergo rotational dynamics that can have long-term consequences. The principle behind this is similar. Just as tidal friction affects the Earth and the Moon, it also impacts the rotation of galaxies. In both cases, the motion of massive bodies, whether it's Earth or the stars in a galaxy, experiences frictional forces that gradually change their dynamics over time. Just as tidal friction leads to the Moon's slow drift away from Earth, it's these same types of forces that could, in the far future, influence the movement and structure of galaxies, potentially even altering the course of galactic evolution. A related concept to consider is the Laplace-Tisserand criterion, which was developed by mathematicians Pierre-Simon Laplace and François Tisserand in the early 19th century. This criterion is used to understand the orbital dynamics between multiple bodies in a system, particularly in celestial mechanics. It explains how bodies like planets and moons interact gravitationally over time, affecting their orbits and relative distances. The Laplace-Tisserand criterion doesn't just apply to the Earth-Moon system, but is also relevant to other celestial bodies, like the interactions between Jupiter and its moons, or the gravitational interactions in binary star systems. It highlights how small changes in the positions or velocities of these bodies can lead to long-term shifts in their orbits, affecting everything from the length of days to the distance between objects in space. When we apply this concept to the Earth-Moon system, it becomes clear how the gravitational interactions, including tidal friction, will continue to affect their long-term relationship. Over millions of years, the Moon will continue to drift farther away from Earth, and the length of a day will continue to increase. In fact, scientists have already discovered evidence that the Earth's day was once much shorter than it is today. For example, around 400 million years ago, the length of a day was only about 22 hours, significantly shorter than the 24 hours we're used to today. However, the effects of tidal friction aren't limited to Earth alone. When we look at the broader picture, we can also consider the way tidal interactions might influence space-time itself, an idea that has been explored by the brilliant physicist Roger Penrose. Penrose, known for his contributions to the understanding of black holes and the nature of spacetime, has suggested that gravitational interactions like those between Earth and the Moon might not only affect the physical motion of objects but also the very fabric of spacetime. Tidal forces could, in this sense, be seen as a manifestation of the way energy flows through the universe, bending and shaping spacetime in ways that are often hidden from direct observation. Penrose's work on spacetime has led to a deeper understanding of how gravity shapes the universe, and tidal friction could be a small yet significant part of this broader picture. As tidal friction slows Earth's rotation and moves the Moon farther away, it's not just a mechanical process. It's an interaction that could have long-term effects on the structure of spacetime itself. While these effects are subtle and only observable over vast periods, they hint at a deeper interconnected relationship between matter, energy, and the fabric of the universe. Another way to explore the long-term implications of tidal friction is through the research of James Peebles, a cosmologist who has helped shape our understanding of the universe's evolution. Peebles has studied how small, gradual forces can accumulate over time to influence the large-scale movement of galaxies and the distribution of matter in the universe. Just as tidal friction affects Earth's rotation and the Moon's orbit, the accumulation of small gravitational forces can influence the structure and movement of galaxies. Tidal forces within galaxy clusters, for instance, can alter the orbits of stars, and over billions of years these interactions can reshape the galaxies themselves. This perspective helps us see that tidal friction, though most noticeable within the Earth-Moon system, is part of a broader cosmic phenomenon that can affect celestial bodies on a galactic scale. The Earth-Moon system is not an isolated case. It's one example of how tidal forces, small and seemingly insignificant in the short term, can have profound long-term effects on the dynamics of space. From the gradual movement of the Moon away from Earth to the eventual slowing of Earth's rotation, tidal friction is a reminder of the delicate balance that governs the universe. It's a force that stretches across time, influencing everything from the movement of the oceans to the motion of galaxies. Understanding this process not only helps us appreciate the forces shaping our planet, but it also reveals the interconnectedness of all things in the universe, from the smallest molecules to the largest cosmic structures. Tidal friction, in its quiet yet persistent way, is one of the forces that continuously molds the future of our world and beyond. Tides play a significant role in shaping ecosystems, and the intertidal zones where the land meets the ocean are some of the most dynamic and diverse environments on Earth. These zones are not just transitional spaces between water and land, they are vital ecosystems that support a wide variety of life forms, many of which are adapted specifically to the rhythms of the tides. This relationship between life and tidal movements may even extend back to the earliest stages of life on Earth. Lynn Margulis, an influential biologist, introduced the endosymbiotic theory, which suggests that life, particularly complex life, evolved through the merging of different species to form symbiotic relationships. In this context, it's fascinating to think that the rhythms of the tides may have influenced the evolutionary process itself, with early life forms adapting to the rise and fall of the oceans, creating ecosystems that thrive in these changing environments. As life evolved, certain species began to rely more directly on tidal rhythms. The intertidal zones, with their constantly changing conditions, provided a unique opportunity for species to adapt and thrive. Over time, these rhythms influence not just the behavior of individual organisms, but the very structure of ecosystems themselves. These tidal ecosystems, where the water level fluctuates throughout the day, offer a perfect example of how life has evolved in response to the environmental patterns set in motion by the Moon. For example, the tidal cycles dictate when organisms like mussels, crabs, and barnacles can feed, breed, and avoid predators, creating a finely tuned balance within these habitats. One of the key factors in the diversity and richness of tidal ecosystems is the role they play in maintaining biodiversity. E.O. Wilson, an eminent biologist known for his work on biodiversity and ecology, emphasized the importance of preserving natural habitats like intertidal zones. These areas, constantly shaped by tidal movements, provide habitats for a wide range of marine species. The cyclical nature of tides ensures that these ecosystems are dynamic and ever-changing, and this variability is crucial for maintaining a variety of life. In the intertidal zone, species must adapt to constantly shifting conditions, such as the availability of food, exposure to air and sunlight, and the presence of predators. This constant ebb and flow creates a mosaic of microhabitats, each with its own distinct ecological conditions. Species living in these zones must therefore be highly specialized to survive and reproduce in this ever-changing environment. Humans, too, have a long history of adapting to tidal rhythms. As societies developed along coastlines, the tides became central to many aspects of daily life. In his book Collapse, Jared Diamond examines how societies throughout history have relied on tidal patterns for agriculture, fishing, and transportation. Coastal communities have long depended on the predictable nature of the tides for harvesting resources. Fishermen, for instance, have long used tidal patterns to determine the best times to fish, taking advantage of the tides to access areas where fish gather or to avoid areas where dangerous currents exist. Similarly, early agricultural societies near coastlines have relied on tidal movements to irrigate fields, especially in estuarine areas where the flow of seawater into freshwater systems can provide essential nutrients for crops. Tides also played a crucial role in the development of ancient trade routes. Early maritime societies, from the Phoenicians to the Polynesians, navigated the seas by reading tidal patterns, using the rise and fall of the waters to predict the most efficient and safe routes. This reliance on tidal movements for navigation underscores how deeply interconnected human societies have always been with the rhythms of the oceans. The ebb and flow of tides provided not just a natural resource, but a way to structure and guide human activity, influencing everything from settlement patterns to trade routes to the development of early maritime technologies. The migratory behavior of animals, too, has been shaped by the tides. Some species, like the elephant seal, demonstrate a fascinating connection between their movements and tidal rhythms. Elephant seals, for example, are known to migrate vast distances, but their movements are often timed with the rising and falling of the tides. These seals rely on the tides to navigate the coastlines they inhabit, using the high tides to haul themselves onto the beaches for rest or to give birth. At lower tides, they return to the sea, following the rhythmic pulse of the ocean that dictates their daily and seasonal routines. This connection between tidal cycles and migratory patterns illustrates how the natural world has evolved to synchronize with the forces of the oceans. Beyond individual species, tidal cycles have had profound impacts on the long-term evolution of life on Earth. One of the most intriguing aspects of the Earth-Moon relationship is the phenomenon of tidal locking. Over time, the gravitational forces between Earth and the Moon have caused the Moon to become tidally locked, meaning it always shows the same face to Earth. This synchronization is a result of the tidal friction between the two bodies. In the distant future, Earth too could become tidally locked to the Moon, meaning that one hemisphere of Earth would always face the Moon, and the other would be in constant darkness. While this process will take billions of years, it raises interesting questions about how the tidal forces that have shaped our planet will continue to influence life on Earth and even the structure of the planet itself. Tidal locking, as an evolutionary phenomenon, may not only affect the relationship between Earth and the Moon, but could also influence the evolution of life itself. As the Moon continues to move away from Earth, the tidal effects we experience today will gradually become weaker, potentially altering the way life forms adapt to the changing environment. This long-term shift in tidal forces could have unforeseen consequences for ecosystems, influencing everything from species migration patterns to the structure of coastal habitats. The relationship between tides and life on Earth is an extraordinary example of how nature's rhythms shape the course of evolution. From the smallest marine organisms that have evolved to thrive in intertidal zones, to the large-scale effects of tidal forces on the migration patterns of species, the influence of the tides is far-reaching. And as we continue to study the ways in which tides impact ecosystems and evolutionary processes, we are reminded that even the most familiar natural phenomena, like the rise and fall of the sea, are intricately connected to the larger forces that shape our world. The tides are not just a daily occurrence, but a key player in the ongoing dance between life and the planet's natural rhythms. Tides are not unique to Earth. In fact, tidal forces are a widespread phenomenon throughout the solar system, acting on moons, planets, and even distant stars. Some of the most intriguing examples of tidal effects are seen on moons like Europa, one of Jupiter's many satellites, and Titan, Saturn's largest moon. These celestial bodies, despite being light years away from Earth, offer fascinating insights into how tidal forces can shape the conditions necessary for life. Carolyn Porco, a renowned planetary scientist, and John Barros, an expert on astrobiology, have explored the idea that tidal heating, driven by gravitational interactions between moons and their host planets, could provide the necessary energy for life-supporting conditions in distant parts of the solar system. Europa, for example, is believed to harbour a vast ocean beneath its icy crust. Tidal forces from Jupiter's immense gravity, combined with the gravitational interactions between Europa and its neighbouring moons, create enough friction within Europa's interior to generate heat. This heat could keep the ocean beneath the surface warm, potentially providing an environment that could support microbial life. The tidal heating process is thought to be a major factor in sustaining a liquid water ocean, a crucial ingredient for life as we know it. Similarly, Titan, with its thick atmosphere and methane-rich lakes, experiences tidal effects as Saturn's gravity pulls on the Moon. These forces cause Titan's surface to flex and shift, possibly generating internal heat. The presence of liquid methane and ethane lakes on Titan suggests that it may have the potential to support life, albeit life quite different from what we find on Earth. Tidal heating could be a crucial factor in making Titan's harsh, frozen surface more hospitable by providing the energy necessary to drive complex chemical reactions. Tidal heating extends far beyond moons in our solar system. Stephen Hawking, one of the most influential physicists of the 20th century, studied the effects of gravity on extreme objects like black holes and neutron stars. These objects, with their intense gravitational fields, create tidal forces so powerful that they distort space-time itself. Hawking's work on black holes revealed how tidal forces could influence not only the objects involved, but also the fabric of the universe. For example, the extreme tidal effects near a black hole can stretch and distort objects in a process known as spaghettification. In such regions of space, gravity is so strong that it warps the space around it, causing even light to bend. These tidal forces are a dramatic demonstration of how gravity operates on both a planetary and a cosmic scale. But what if tidal forces could stretch beyond the realms of our own universe? Lisa Randall, a leading theoretical physicist, has proposed ideas about the multiverse, suggesting that our universe might be just one of many, each with its own set of physical laws. In her research, Randall explores the possibility that tidal forces might exist in other dimensions that operate under entirely different sets of rules. If such forces exist, they could influence the behavior of galaxies, stars, and even life forms in ways that are beyond our current understanding of physics. Imagine for a moment that the tides we experience on Earth are just one manifestation of much grander cosmic tidal forces that ripple through multiple dimensions, creating patterns we have yet to discover. This notion opens up an exciting possibility that the tidal forces we observe on Earth are just a small, localized example of a much more universal phenomenon. Now let's step back to our own solar system. Earth's tides, shaped by the Moon's gravitational pull, offer us a familiar example of how tidal forces work. But how do tides on other celestial bodies compare? For example, Mars has two small moons, Phobos and Deimos, which experience tidal forces from the planet. However, these moons are much smaller than our Moon, and their proximity to Mars creates tidal effects that are considerably weaker. This means that the Martian tides are much less pronounced, and the potential for tidal heating or significant tidal effects on Mars's surface is minimal. However, scientists are exploring whether the tidal forces from Mars's moons could influence its geology or its atmosphere in ways we don't yet fully understand. In contrast, moons like Europa, Titan, and even our own Moon exhibit tidal effects that can have a profound impact on their geological and environmental processes. Tidal forces shape not only the oceans but also the surface of moons. On Europa, the interaction with Jupiter's gravity creates fractures in the icy surface, allowing water from beneath to emerge in plumes, a process called cryovolcanism. This constant tugging and stretching may create the conditions needed to sustain liquid water and possibly even life beneath the ice. Similarly, on Titan, the tidal forces may cause the surface to shift, allowing for the movement of liquids and the potential for complex chemical processes. The effects of tidal forces also extend to the geology of planets and moons. Hal Leveson, a planetary scientist, has studied how tidal forces can influence the movement of celestial bodies within our solar system. Leveson's research suggests that these forces play a significant role in shaping the orbits of moons and planets, potentially altering their paths over long periods. In some cases, tidal forces can even trigger volcanic activity, as the stress caused by gravitational interactions causes fissures and cracks in the surface. This process is not limited to Earth's moon or even to the moons of gas giants. It is a universal phenomenon that could have implications for the formation and evolution of planetary bodies across the universe. These tidal forces, while they may seem subtle or distant, are a fundamental part of the cosmic dance that shapes the universe. From the potential for life on Europa and Titan, to the extreme forces near black holes and neutron stars, tidal forces remind us that gravity is more than just a pull between two objects. It's a force that ripples through space, affecting everything from the tiniest moons to the largest galaxies. As we continue to explore the far reaches of our solar system and beyond, we are bound to uncover even more ways that tides shape the universe, reminding us of the deep interconnectedness between all things in the cosmos. The moon's gravitational pull does far more than just create the tides we observe every day. Over geological timescales, its influence has shaped the very nature of Earth's climate, affecting everything from temperature patterns to sea levels. This constant tug on the planet has had a profound and lasting effect on the Earth's systems, acting as both a stabilizing force and a driver of long-term climate shifts. One of the most significant impacts the moon has had on Earth's climate is through its effect on the planet's axial tilt. Earth's axis is tilted at an angle of approximately 23.5 degrees, which plays a critical role in the planet's seasons. However, this tilt is not fixed. It shifts slightly over time, a phenomenon that is influenced by the moon's gravitational pull. This long-term change in tilt, referred to as axial precession, is one of the key factors that contributes to the natural climate cycles we see on Earth. James Hansen, a climate scientist well known for his work on global warming, has developed models that show how Earth's climate can be influenced by various factors, including tidal forces. In his research, Hansen integrates tidal forces into the broader context of global temperature and ocean behavior. His work suggests that the moon's gravitational pull, while small in comparison to other factors like greenhouse gases, has nonetheless played a subtle yet significant role in shaping long-term climate patterns. The tidal forces exerted by the moon influence ocean currents, which in turn impact the distribution of heat around the planet. These currents help to regulate global temperatures, preventing regions from becoming too hot or too cold. In a sense, the moon has acted as a stabilizing force, moderating Earth's climate for millions of years. As the global climate changes, rising sea levels due to melting ice and thermal expansion are now a significant concern. This rise in sea levels interacts with the moon's tidal forces in ways that could exacerbate coastal flooding. While the moon's gravitational pull continues to drive the tides, the rising sea levels mean that high tides can now push further inland, flooding areas that were once safe from the ocean's reach. This is especially concerning for coastal communities around the world, as even small increases in sea level can have large impacts on flooding during high tide events. As the oceans rise, the tidal forces that once provided a natural rhythm to the water's movement are now contributing to more frequent and intense flooding, a situation that will likely worsen in the coming decades. In addition to the moon's immediate influence on Earth's oceans, there is also a longer-term connection between tidal forces and Earth's climate through the Milankovitch cycles. These cycles, named after Serbian scientist Milutin Milankovic, refer to the gradual changes in Earth's orbit and axial tilt that occur over tens of thousands to hundreds of thousands of years. These cycles are responsible for the ice ages, as the amount of sunlight reaching different parts of the Earth changes with the shifting tilt and orbit. Tidal forces play a role in maintaining Earth's axial tilt and orbital eccentricity over time, influencing these cycles and the long-term behavior of the planet's climate. The moon helps to stabilize Earth's tilt, preventing drastic changes that could lead to more extreme fluctuations in climate. Without the moon's gravitational influence, Earth's tilt could vary much more than it does, potentially causing far more dramatic shifts in climate. The moon also plays a role in maintaining Earth's equatorial bulge. Due to Earth's rotation, the planet isn't a perfect sphere, but instead is slightly flattened at the poles and bulging at the equator. This bulge is influenced by the tidal forces between Earth and the moon. The moon's gravitational pull causes Earth's oceans to rise at the equator, creating a sort of tidal bulge that moves as the Earth rotates. This equatorial bulge affects ocean currents, as water is constantly moving to accommodate the changing tidal forces. These currents, in turn, have an impact on the distribution of heat around the planet, which plays a crucial role in shaping global weather patterns. The Moon's influence on the equatorial bulge also affects atmospheric circulation, which in turn drives weather systems across the globe. In this way, the Moon's gravitational pull is intricately connected to the systems that regulate Earth's climate, from ocean currents to atmospheric circulation. The energy that is transferred through tidal forces helps to maintain a delicate balance that keeps our planet habitable. As the Moon slowly moves farther away from Earth, the influence it has on the planet's climate and the oceans will gradually diminish. This will take billions of years, but the long-term effects could ultimately alter Earth's climate in ways we can't fully predict yet. In summary, the Moon's influence on Earth's climate and sea levels is far more profound than the tides alone. From stabilizing the planet's axial tilt to influencing ocean currents and atmospheric circulation, tidal forces are key to understanding the long-term patterns of Earth's climate. As we face the challenges of rising sea levels and climate change, it is important to recognize the ways in which the Moon's gravitational pull has shaped and continues to shape the planet's environment. The complex interaction between the Moon's tides and Earth systems reminds us that the forces at work on our planet are interconnected and vast, stretching from the smallest fluctuations in sea level to the grand cycles that govern Earth's climate over millennia. Tidal energy, a powerful and renewable resource, harnesses the natural motion of the oceans to generate electricity. The concept of using tides as a source of power dates back centuries, and one of the earliest pioneers in this field was George Forster. In the late 1800s, Forster developed one of the first tidal mills, a simple but effective mechanism that used the rise and fall of tides to turn a wheel and grind grain. This early technology, while basic, demonstrated the immense potential of tidal forces as a reliable and consistent energy source. Since then, the field of tidal energy has evolved significantly, with modern projects now harnessing the power of the tides to provide renewable electricity to homes and businesses around the world. Today, tidal energy is being explored and developed in various parts of the world, with notable projects in the United Kingdom and Canada. In the UK, the world's first commercial tidal power station, the Severn Barrage, has been proposed, aiming to use the powerful tidal range in the Severn Estuary to generate electricity. The area has one of the highest tidal ranges in the world, making it an ideal location for tidal energy production. Similarly, Canada has invested in tidal energy projects along its Atlantic coast, particularly in places like the Bay of Fundy, known for having some of the highest tides in the world. These regions offer an abundance of untapped potential, where the natural movements of the ocean could be harnessed to produce clean, sustainable power. Despite the promise of tidal power, there are still significant challenges to overcome. Technologically, the development of tidal energy infrastructure is complex and expensive. Tidal power plants often require large, sophisticated turbines or dams that can withstand the immense forces of the ocean. These projects also need to be designed with careful consideration for the surrounding environment. The impact of large-scale tidal energy installations on local ecosystems, particularly marine life, is a critical concern. Turbines and other infrastructure could disrupt the natural habitats of fish, seals, and other species that rely on these coastal areas. Balancing the need for renewable energy with environmental preservation is one of the ongoing challenges of tidal power development. One of the leading advocates for renewable energy, Emery Lovins, has highlighted the potential of tidal power as part of a broader strategy to transition away from fossil fuels. Lovins, who has long championed sustainable energy, sees tidal energy as a key piece of the puzzle in creating a clean, sustainable energy future. Unlike solar and wind energy, tidal power has the advantage of being more predictable. While the sun and wind can be intermittent, tidal patterns are highly reliable as they are driven by the gravitational forces of the moon and sun. This reliability makes tidal energy an appealing option for countries looking to diversify their energy sources and reduce their reliance on fossil fuels. However, as with all forms of renewable energy, tidal power is not without its challenges. The infrastructure required to harness tidal energy is costly to build and maintain. The turbines or barriers used to capture tidal power must be able to withstand the harsh conditions of the ocean, including strong currents, saltwater corrosion, and extreme weather events. Furthermore, many of the most promising tidal energy sites are located in remote areas, making transportation and construction even more difficult. Despite these challenges, ongoing technological advances are making tidal energy more feasible, with smaller, more efficient turbines and more affordable construction methods being developed. Another challenge of large-scale tidal energy projects is their potential impact on local tidal patterns and ecosystems. Tidal power plants, especially those that involve dams or barriers, can alter the natural flow of water and disrupt the ecosystems that depend on it. For example, the construction of a tidal barrage could affect the movement of fish and other marine species, potentially blocking their migratory paths or disrupting breeding grounds. The creation of artificial tidal patterns might also have unintended consequences on coastal erosion or sediment transport. As with any major infrastructure project, careful environmental assessments are necessary to ensure that the benefits of tidal energy outweigh the potential harm to local ecosystems. Despite these challenges, the potential benefits of tidal energy are undeniable. If harnessed correctly, tidal power could provide a significant amount of renewable energy, helping to reduce greenhouse gas emissions and combat climate change. Unlike fossil fuels, tidal energy doesn't produce harmful pollutants or contribute to global warming. Additionally, tidal power is highly reliable, producing electricity consistently throughout the year, day and night, thanks to the predictable nature of tides. This makes it an excellent complement to other renewable energy sources, such as wind and solar power, which can be more variable. As the world looks for ways to transition to cleaner energy sources, tidal power offers a promising solution. The ocean's rhythmic rise and fall may one day provide a significant portion of the energy needed to power our homes and industries. While there are still many hurdles to overcome, including technological challenges and environmental concerns, the potential for tidal energy to contribute to a sustainable clean energy future is exciting. With continued research and development, tidal power could become a key player in the global effort to reduce our reliance on fossil fuels and mitigate the effects of climate change. Harnessing tidal energy is a challenge, but it's a challenge worth pursuing. As we look toward the future, we can be hopeful that advances in technology and a growing commitment to sustainability will allow us to tap into the immense power of the oceans. By doing so, we can not only reduce our carbon footprint but also ensure that future generations inherit a world where energy is clean, abundant, and in harmony with nature. The moon's gravitational pull doesn't just create the tides we see at the shore. It also plays a key role in shaping ocean currents, which in turn influence global weather patterns. The impact of tidal forces on ocean currents can be traced back to the pioneering work of Matthew Fontaine Maury, a 19th century oceanographer who is often referred to as the father of modern oceanography. Maury studied the movement of ocean currents, mapping the flow of water across the globe and revealing the powerful influence of tides on these currents. Maury's early observations showed that the ocean surface is not a still, static body of water, but a dynamic system driven by both wind and tidal forces. The tides create periodic variations in ocean currents, which, like an invisible engine, drive the movement of water around the world. These tidal currents help to distribute heat across the planet, making the Earth's climate more balanced and consistent. Tidal forces can cause shifts in the direction and strength of ocean currents, which influences everything from temperature to the distribution of nutrients in the ocean, affecting marine life and ultimately global weather patterns. One of the most profound ways in which tides influence weather is through their relationship with climate phenomena like El Niño and La Niña. These events, which involve changes in the temperature of surface waters in the Pacific Ocean, have far-reaching effects on global weather, from droughts to floods. The relationship between tides and these large-scale climate patterns is complex, but tidal forces help shape ocean circulation, which plays a role in the conditions that give rise to El Niño and La Niña. The movement of warm and cold water, influenced by tides, helps set the stage for these dramatic shifts in climate, which can disrupt weather patterns across the globe. For example, during an El Niño event, warm water in the central Pacific Ocean shifts eastward, altering weather patterns across the Americas and beyond. The shifting of ocean currents during this time is influenced by the tidal forces that push and pull on the water. The connection between tides and the ocean currents that lead to El Niño highlights the interconnectedness of Earth's systems, and how tidal forces are one of many factors contributing to global climate patterns. Similarly, the opposite, La Niña, which is characterized by cooler than usual sea surface temperatures in the central Pacific, can also be influenced by changes in the ocean currents driven by tidal forces, although other atmospheric and oceanic factors also play a role. The moon's pull on Earth doesn't just affect the ocean surface waters, it extends into the deeper currents that flow throughout the world's oceans. These deep currents, which help regulate the distribution of heat and nutrients, are also influenced by tidal forces. As the tides push and pull on the surface of the oceans, they create movements in deeper water layers, driving what is known as thermohaline circulation. This global conveyor belt of water helps to regulate climate by moving warm water from the equator to the poles and cold water from the poles back to the equator. These currents are crucial for maintaining a stable climate, and tidal forces play a subtle but significant role in keeping them moving. In addition to influencing ocean currents, the Moon's gravitational pull also affects atmospheric conditions. Eugene Feibelman, a researcher in atmospheric sciences, explored how the movement of ocean currents driven by tidal forces could influence wind patterns and weather systems. As the oceans shift and change with the tides, they release heat into the atmosphere, affecting air pressure and creating the conditions for wind and precipitation. This means that tidal forces are not only shaping the oceans, but are also influencing the atmosphere, impacting weather patterns in ways that we're still working to fully understand. The study of tidal influences on both ocean currents and atmospheric conditions has become increasingly important in the field of climate science. Scientists are using advanced models to predict how changes in tidal forces, whether due to shifting patterns in the Moon's orbit or rising sea levels from climate change, could impact future weather events. These models take into account the subtle but significant effects that tides have on ocean circulation, atmospheric pressure, and global climate systems. As climate change continues to affect global weather patterns, understanding the role of tides in these systems is becoming more important than ever. One of the ways in which tidal forces could impact future weather events is by influencing the intensity and frequency of storms. As sea levels rise and tidal ranges increase, coastal areas will be more susceptible to flooding, especially during high tides or storm surges. The interaction between tidal forces and storm systems could lead to more extreme weather events, with higher tides exacerbating the effects of hurricanes, typhoons, and other storms. Tidal forces could also influence the behavior of ocean currents, potentially altering the paths of storms and shifting weather patterns in ways that are difficult to predict. The connection between tides and weather is a reminder of how everything on Earth is interconnected. Tidal forces, though they may seem like small, predictable movements, are a powerful force that shapes not only the oceans, but also the atmosphere and climate. From the movement of ocean currents to the regulation of heat and nutrients, tidal forces play a vital role in maintaining the stability of Earth's climate systems. As we continue to study the impact of tides on global weather, we gain a deeper understanding of the delicate balance that exists within the Earth system and the ways in which even small forces can have profound effects on the world around us. Tidal forces are not just responsible for the movement of the oceans, they also play a significant role in shaping the Earth's surface. The gravitational pull of the Moon, and to a lesser extent the Sun, stretches and compresses the Earth, causing subtle but powerful deformations in the planet's crust. These tidal deformations may seem like minor fluctuations, but over geological timescales, they can contribute to the movement of tectonic plates, influence fault lines, and potentially even trigger earthquakes. The Earth's crust is constantly shifting and adjusting due to the movement of tectonic plates. The theory of plate tectonics explains how the Earth's outer shell is broken into several large and small pieces, which float on the semi-fluid layer of the mantle beneath. These plates are in constant motion, slowly drifting apart or colliding, which results in the formation of mountain ranges, earthquakes, and volcanoes. While tectonic forces are the primary drivers of these geological processes, tidal forces add a subtle but continuous influence. The Moon's gravitational pull creates periodic stretching and compressing of the Earth's crust, which can influence the movement of tectonic plates, especially along fault lines. Fault lines, which are fractures in the Earth's crust where tectonic plates meet, are particularly sensitive to tidal forces. The Moon's pull can slightly alter the pressure along these faults, making them more prone to slipping, especially if the fault is already under stress. This means that, in theory, tidal forces could contribute to the triggering of earthquakes. While tidal forces are unlikely to cause a major earthquake on their own, they can certainly play a role in triggering an event when conditions are right. This interplay between tidal forces and tectonic movement reminds us that the forces shaping our planet are not only grand and slow-moving, but also small and rhythmic, working in tandem over millions of years. To understand how tidal forces influence geological processes, we can look to Charles Lyell, a geologist in the 19th century who is best known for his development of the theory of uniformitarianism. Lyell's theory posits that the Earth's geological processes are gradual and have been operating in the same manner throughout Earth's history. His famous idea, "the present is the key to the past," suggests that by studying current processes, we can understand how the Earth's surface has evolved over time. In the context of tidal forces, Lyell's theory helps explain how small, regular changes in the Earth's crust, such as those caused by the Moon's gravitational pull, can accumulate over vast periods to shape the planet's surface in significant ways. Tidal forces are an example of how uniform, consistent natural processes can result in major geological changes over long timescales. Each tide causes a tiny, almost imperceptible deformation in the Earth's crust, but these deformations, occurring millions of times a year, add up. Over millions of years, this cumulative effect can influence tectonic movements, especially in areas that are already geologically active. Another fascinating aspect of the Earth-Moon system is tidal locking. Tidal locking is a process in which one body's rotation slows over time due to the gravitational interactions with another body, eventually causing the two to become synchronized. The Moon is currently in tidal lock with Earth, meaning that one side of the Moon always faces our planet. This synchronization happens because of the constant tidal friction between Earth and the Moon. As the Earth's rotation slows, the Moon gradually drifts away from Earth, moving at a rate of about 4 centimeters per year. Over billions of years, this process will cause the Earth to become tidally locked to the Moon, meaning that one side of Earth will always face the Moon. This effect, though far in the future, will have significant implications for the Earth-Moon system, and potentially for Earth's geological processes. The process of tidal locking may also have far-reaching effects on Earth's geological behavior. As the Moon continues to move away from Earth, the tidal forces it exerts on the planet will gradually weaken. This could affect Earth's geological activity, including the movement of tectonic plates and the intensity of earthquakes. The gradual weakening of tidal forces may lead to changes in the rate of plate movement and the frequency of certain geological events. While this process will take billions of years, it underscores how even subtle, long-term changes in the Moon's position can influence the Earth's geology. Tidal forces are also believed to play a role in volcanic activity, especially in geologically active regions like the Ring of Fire, a major area of volcanic activity that encircles the Pacific Ocean. The Moon's gravitational pull can cause stress and deformation along fault lines, as well as in volcanic regions. These forces might not directly trigger volcanic eruptions, but they can influence the movement of magma beneath the surface, contributing to volcanic activity over time. In places like the Ring of Fire, where tectonic plates are constantly interacting, tidal forces can subtly impact the movement of magma, potentially increasing the likelihood of eruptions in certain areas. The idea that tidal forces could influence volcanic activity is part of a broader understanding of how interconnected Earth systems are. The Earth's geology is not just shaped by sudden, catastrophic events like earthquakes or eruptions. It's also influenced by the constant rhythmic forces of the Moon and the Sun. Over time, these forces add up, creating an ongoing interaction between the Moon's gravitational pull and the movements of Earth's crust. This interaction helps shape the planet's surface in ways that are sometimes difficult to observe in the short term but become clear over geological timescales. In summary, tidal forces play a much more significant role in shaping Earth's surface than we might initially realize, from influencing tectonic movements and fault lines to potentially contributing to volcanic activity. The Moon's gravitational pull is a subtle but powerful force in the planet's geological processes. As Earth's rotation gradually slows and the Moon drifts away, the influence of tidal forces will continue to shape the planet's surface, altering the dynamics of the Earth-Moon system and influencing our world for billions of years to come. Tides, then, are not only responsible for the rise and fall of the oceans, but also for the slow but steady transformation of Earth's crust, a testament to the enduring power of the Moon. Tidal cycles, with their regular and predictable rhythms, have long been used as a natural clock by civilizations across the world. Before the advent of mechanical clocks and precise timekeeping, people relied on the ebb and flow of the tides to measure time, especially for practical purposes like agriculture, fishing, and navigation. Ancient cultures, from the Sumerians to the Greeks, understood the importance of tidal cycles in managing the rhythms of daily life. The tides, influenced by the gravitational pull of the Moon, offer a consistent pattern that humans could use to organize their activities. In many coastal communities, the daily tidal cycle helped to establish routines, marking time for when to plant crops, when to fish, or when to set sail. The close relationship between the moon's movements and the Earth's tides made the moon an important factor in early calendars. Many ancient civilizations, including the Babylonians, Egyptians, and Chinese, based their calendars on lunar cycles. A lunar calendar tracks the phases of the moon and is tied directly to the rhythm of the tides. Since the moon's gravitational influence causes tides to follow a cyclical pattern, these societies aligned their calendars with the moon's movements to structure the passage of time. The result was a system that connected daily human life to the vast cosmic rhythms of the universe. In fact, the way tidal cycles work offers a fascinating insight into the connection between tides and time itself. Tidal friction, the process by which the gravitational interaction between Earth and the moon gradually slows the Earth's rotation, has been instrumental in shaping both the Earth's day and the length of the tidal cycle. As the moon's gravity pulls on Earth's oceans, it creates a frictional force that gradually slows down the Earth's spin. This effect, though small day to day, adds up over long periods. Over millions of years, Earth's rotation has been slowly decelerating, and the days have grown longer. In the past, days on Earth were much shorter, and as the moon moves farther from Earth, the length of a day will continue to increase. Lyndon LaRouche, a prominent economist and theorist, explored the relationship between time and gravitation in the context of tidal friction. LaRouche proposed that tidal forces could be viewed as a key component in the flow of time itself. As the Earth slows down and the moon drifts away, the relationship between these two bodies is in constant flux, and this gradual change influences the perception of time over long periods. In this way, tidal friction links the passage of time with the physical movement of celestial bodies, suggesting that time is not just an abstract concept, but a real, measurable phenomenon that is directly tied to the forces at play in the universe. The alignment of tidal cycles with lunar phases also influenced cultural practices and rituals throughout history. Many ancient societies link the phases of the moon with particular activities or events, whether it was for religious observances, agricultural cycles, or even governance. The agricultural calendar in many cultures was closely aligned with the lunar cycle. For instance, the full moon was often seen as an ideal time for planting or harvesting crops, while the new moon signified a time for rest and renewal. This connection between the moon's phases and daily life demonstrates how early human societies observed and integrated the natural rhythms of the Earth and the moon into their understanding of time. Another fascinating aspect of the lunar calendar and its connection to tidal cycles is how the moon's gravitational pull influences not only the Earth's oceans, but also atmospheric conditions. The moon's effect on the tides is not just limited to the water, it extends to the movement of air in the atmosphere. This connection is important because the atmosphere, like the oceans, is governed by the forces that shape Earth's physical systems. As the moon's gravity causes the oceans to bulge and recede, it also has an impact on wind patterns and the distribution of heat around the Earth, subtly influencing the weather. Roger Penrose, a renowned theoretical physicist, offers another intriguing perspective on the relationship between time and tidal movements. Penrose's work on space-time suggests that time is not a linear progression, but something far more complex, linked to the very structure of the universe. He proposed that time could be seen as a fundamental property of the universe, intimately connected with the flow of energy and the dynamics of space-time. If we apply Penrose's ideas to the tidal cycles, we could view the rise and fall of the tides not simply as an event driven by gravity, but as a manifestation of the deeper flow of time itself. The constant motion of the oceans, driven by tidal forces, might reflect a much larger cosmic rhythm, revealing the interconnectedness of all things in the universe. On a more practical level, the study of tidal forces and their connection to time also opens up fascinating possibilities for understanding time at a quantum level. The moon's pull on the Earth causes not just visible, large-scale effects like tides, but also potentially impacts the very fabric of space-time at smaller subatomic scales. As scientists continue to explore quantum mechanics, the relationship between tidal forces and time could provide a new lens through which to study the quantum world. If tidal forces can influence time at the scale of the oceans, who's to say how they might affect the most fundamental particles of matter? This idea remains speculative, but the very notion that the tides could hold the key to understanding time at a quantum level is a thrilling avenue for future research. Over the course of history, the moon's rhythms have been woven into the fabric of human timekeeping and culture. From ancient calendars to modern scientific theories, the connection between tides and time has influenced our understanding of both the natural world and the passage of time itself. Whether through the gradual slowing of Earth's rotation, the alignment of lunar cycles with human activities, or the deeper connections between time and space-time, the tides offer a unique and profound perspective on the universe's ever-moving clock. The next time you watch the tides roll in, remember that they are not just a daily rhythm, but a reminder of the cosmic forces that shape our perception of time. Tidal research plays a crucial role in space exploration, offering invaluable insights into the gravitational dynamics that shape the behavior of moons and planets across our solar system. Understanding tidal forces is not only important for studying Earth's tides, but also for exploring celestial bodies like the Moon, Europa, Titan, and Enceladus, which exhibit similar tidal interactions. These tidal forces, caused by gravitational interactions between a planet or moon and its parent body, can tell us much about the internal structure and dynamics of distant worlds. As we push further into the cosmos, studying tidal forces becomes essential for planning future missions, especially those that may involve lunar bases or space stations. Tidal forces on the Moon, for example, could have a significant impact on future human habitation. Arthur C. Clarke, the legendary science fiction writer and visionary, speculated about the potential for space habitation, including the possibility of constructing bases on celestial bodies like the Moon. Clarke's ideas often revolved around how gravitational forces, especially tidal forces, would affect life on the Moon. For example, the Moon's lack of atmosphere means that temperatures can swing dramatically, from scorching heat during the day to freezing cold at night. This extreme variability, combined with tidal forces, would challenge the construction and sustainability of lunar habitats. Clarke's visionary work highlights the importance of understanding tidal forces not only for technical challenges like energy generation and resource extraction, but also for ensuring the safety and well-being of future astronauts. Tidal forces will also play a role in space stations orbiting the Moon or other celestial bodies. These stations, which will likely be subject to the gravitational influence of nearby planets or moons, will experience slight but constant tidal deformations as they orbit their host bodies. Understanding these forces is critical for designing structures that can withstand this stress over extended periods, ensuring long-term sustainability for missions to the Moon, Mars, or beyond. As we move toward establishing a permanent presence in space, engineers will need to account for the subtle effects of tidal forces on everything from life support systems to spacecraft propulsion. One of the most intriguing aspects of tidal research is its potential to inform the ongoing search for extraterrestrial life. As Neil deGrasse Tyson, the renowned astrophysicist, often emphasizes, the quest for life beyond Earth is not just about looking for planets in the habitable zone, the so-called Goldilocks zone, but also about understanding the conditions that could support life in places where we least expect it. Moons like Europa, one of Jupiter's satellites, and Enceladus, a moon of Saturn, offer compelling examples of how tidal forces could create environments conducive to life. Europa, for instance, is believed to harbour an underground ocean beneath its icy crust. Tidal forces from Jupiter's massive gravity cause Europa's surface to flex and stretch, generating internal heat through tidal friction. This heat may be sufficient to keep the ocean beneath the surface warm, creating the ideal conditions for microbial life. Scientists are exploring whether these moons, heated by tidal forces, could harbour life forms similar to the extremophiles found in Earth's deep ocean vents. The ongoing research into Europa and Enceladus suggests that tidal heating could play a vital role in maintaining liquid water on these moons, which, as we know from life on Earth, is essential for the development of life. In addition to their role in sustaining potential habitats for life, tidal forces can also influence the geological activity on these moons. For example, the same tidal forces that heat Europa's interior could also cause the moon's surface to crack and shift, creating fissures where water may be able to escape into space. This process, called cryovolcanism, could provide scientists with valuable clues about the internal composition of Europa and whether it harbours conditions suitable for life. Looking beyond the immediate search for extraterrestrial life, tidal forces could also provide new ways of understanding the formation and behaviour of celestial bodies. The study of tidal interactions in our own solar system offers insights into how moons and planets evolve over time. For instance, tidal locking, where a moon always shows the same face to its parent planet, is a result of the Moon's tidal interactions with Earth. Over millions of years, these interactions cause the Moon's rotation to synchronize with its orbit around Earth. By studying tidal locking on other moons in the solar system, scientists can learn more about the long-term evolution of planetary systems and the forces that shape them. Furthermore, the ongoing study of tidal forces could help scientists refine our models of planetary and moon formation. Tidal interactions between a planet and its moons, or between moons and their parent planets, can influence the distance and orbital dynamics of celestial bodies. For example, the gradual movement of the Moon away from Earth due to tidal friction tells us something about the history of our planet's relationship with the Moon, and how their gravitational dance has shaped the Earth's rotation. Understanding these long-term processes could provide valuable insights into the formation of other planetary systems, potentially even those beyond our solar system. Future space missions will likely rely on tidal science to unlock even more mysteries about the cosmos. For instance, missions to Titan, Saturn's largest moon, could provide new information about how tidal forces affect planetary atmospheres. Titan has a thick atmosphere composed primarily of nitrogen, but the interaction between Titan's atmosphere and its oceans could be influenced by the tidal forces exerted by Saturn. By studying these forces, scientists could learn more about the weather systems on Titan and gain insights into the complex interactions between oceans, atmosphere, and gravity. The role of tides in space exploration and the search for extraterrestrial life is vast and varied. Whether it's understanding how tidal forces influence the internal heat of moons like Europa, shaping the environments where life might exist, or studying tidal interactions to gain insights into the formation and behavior of celestial bodies, tidal science is essential to our exploration of the universe. As we look toward future space missions, the study of tides will be a key tool in unlocking the mysteries of the cosmos and guiding us toward new frontiers in our search for life beyond Earth. The Moon has been a constant companion to Earth for billions of years, influencing everything from our tides to the stability of our planet's axial tilt. Yet, despite its essential role, the Moon's fate is not one of permanence. Over long periods, tidal friction, the interaction between Earth's oceans and the Moon, causes the Moon to slowly drift away from Earth. This gradual process, although imperceptible in human timescales, has profound implications for the future of the Earth-Moon system and the tides that shape our planet. Tidal friction occurs because of the gravitational interaction between the Earth and the Moon. As the Moon's gravity pulls on Earth's oceans, it creates tidal bulges that stretch the planet's surface. However, because Earth is rotating faster than the Moon orbits, these tidal bulges are not perfectly aligned with the Moon's position. This misalignment causes friction between the ocean and the Earth's crust, slowly transferring Earth's rotational energy into the Moon's orbit. As a result, Earth's rotation is gradually slowing, and the Moon is slowly moving away from Earth at a rate of about 4 centimeters per year. This might seem like a small distance, but over millions of years it adds up, and the Moon will continue to drift farther from Earth. This process has been happening for billions of years, and it is linked to some fascinating ideas in cosmology. Gerard K.T. Hooft, a Nobel laureate in physics, has explored the long-term evolution of celestial systems, suggesting that tidal forces can influence the dynamics of not just the Earth-Moon system, but also the broader evolution of planetary systems. The gradual separation of Earth and the Moon is part of a larger, ongoing process that affects the stability and behavior of all gravitationally bound systems. Tidal interactions, as Hooft's work suggests, are not just important for understanding Earth and its Moon, but can provide insights into the fundamental forces that govern the movement of celestial bodies throughout the universe. As the Moon drifts farther from Earth, the most immediate effect will be on the tides. The strength of tidal forces depends on the distance between the Earth and the Moon. The closer the Moon is to Earth, the stronger its gravitational pull on the oceans. As the Moon moves farther away, the tides will become less pronounced, and the daily rise and fall of the oceans will diminish over millions of years. This gradual weakening of the tides will have a profound impact on Earth's environment. Tides are crucial for maintaining ecosystems, especially in coastal regions where the rise and fall of the water shapes habitats and supports biodiversity. Over long periods, weaker tides could change the dynamics of these ecosystems, potentially leading to shifts in marine life and coastal environments. One of the most intriguing aspects of the Earth-Moon system is the concept of tidal locking. Tidal locking is a process in which the rotation of a planet or moon gradually slows until it matches the orbital period of the object it is gravitationally bound to. This is already happening with the Moon. It takes the same amount of time for the Moon to rotate on its axis as it does to orbit Earth, which is why we always see the same side of the Moon. As the Earth's rotation continues to slow down and the Moon moves farther away, the Earth itself may eventually become tidally locked to the Moon. This means that billions of years from now, one hemisphere of Earth would always face the Moon, while the other would remain in perpetual darkness. The consequences of tidal locking would be significant for Earth's climate and environment. If Earth were to become tidally locked to the Moon, it could lead to extreme changes in temperature distribution. The side of Earth facing the Moon would experience constant daylight, while the far side would be in constant darkness. This could create intense temperature differences between the two sides, potentially making the planet less hospitable for life. The dynamics of the Earth-Moon system would fundamentally change, and with it, the patterns of tidal behavior that have been a steady feature of Earth's environment. As the Earth-Moon system continues to evolve, the weakening of tidal forces will also affect the geological processes on Earth. Tidal forces contribute to the movement of Earth's tectonic plates, and as these forces decrease, the rate of tectonic activity may slow. This could influence volcanic activity, the formation of mountain ranges, and the shifting of continents. The long-term effects of tidal friction on Earth's geological processes are still not fully understood, but the gradual changes in the Earth-Moon system will certainly play a role in shaping the planet's future. The Moon's influence on Earth's climate, tides, and geological processes underscores how deeply interconnected the Earth-Moon system is. The Moon's gradual drift away from Earth may seem like a slow and imperceptible process, but it has profound implications for the future of our planet. Over the course of billions of years, the Earth-Moon system will continue to evolve, with the Moon eventually reaching a point where it will no longer exert the same tidal forces on Earth. While this process is so distant that it is not a concern for humanity in the near future, understanding these long-term changes provides valuable insight into the forces that shape the evolution of planets and moons throughout the universe. The fate of the Moon also serves as a reminder of the dynamic and ever-changing nature of the universe. Just as the Moon has been a steady companion to Earth, its gradual movement away from our planet highlights the ongoing processes of cosmic evolution. The Earth-Moon system, shaped by tidal forces, will continue to evolve over geological timescales, leading to a future that is vastly different from the world we know today. And while the Moon may eventually leave Earth's side, its legacy will live on in the tides, the ecosystems it has shaped, and the long-term evolution of our planet. The study of tidal forces and the Moon's fate reminds us that even the most familiar celestial bodies are part of a much larger and ever-changing cosmic story. The study of tidal forces offers us more than just an understanding of the rise and fall of the oceans. It reveals a deeper connection between the Earth and the Moon, and the intricate cosmic dance that shapes our planet's behavior. Tides are not isolated phenomena but are part of the broader dynamic Earth-Moon system, governed by the gravitational pull of the Moon, the rotation of Earth, and the Sun's influence. Understanding this system is essential not only for predicting tides, but also for appreciating how forces that govern the oceans influence the very structure of our world. The Moon's influence on Earth's tides is a clear example of how celestial bodies, even those far from our planet, shape the environment and life on Earth. The regularity of tides has impacted ecosystems, from coastal habitats to the global climate. They affect everything from nutrient distribution in the oceans to the patterns of migration in marine species. Tidal forces, while subtle, help maintain the delicate balance of life on Earth, influencing ecosystems in ways that might seem invisible, yet are deeply felt in the rhythm of daily life. Tides also shape the Earth's geological processes. The constant pull of the Moon on Earth's oceans causes periodic deformations in the Earth's crust, influencing tectonic movements, fault lines, and even volcanic activity. These small, rhythmic forces, accumulated over millions of years, contribute to the ongoing shaping of the planet's surface, providing a link between Earth's oceans, geology, and the Moon. The Earth-Moon system, therefore, is not just a passive backdrop to human existence, but an active, evolving partnership that has profound impacts on the planet's physical and environmental state. On a more philosophical level, the study of tides connects us to the broader cosmic order. The regularity of tidal cycles, driven by the steady gravitational forces between Earth and the Moon, is a reflection of the larger predictable forces that govern the universe. This cosmic rhythm speaks to the interconnectedness of all natural forces, from the smallest atomic interactions to the largest galactic movements. As we look to the stars, the moon reminds us that the forces shaping Earth are part of a much grander universal dance. Carl Sagan, the renowned astronomer and philosopher, often spoke of the vastness and complexity of the universe, encouraging us to see ourselves as part of something far greater. The tides, though seemingly small and mundane, are a profound reminder of our connection to the cosmos, providing a constant, steady link between Earth and the celestial forces that shape its existence. The moon's enduring influence on Earth's tides also raises fascinating questions about the future. Over millions of years, the moon's gravitational pull will continue to slow Earth's rotation and drive the moon farther away. This process will eventually lead to tidal locking, where one side of Earth will always face the moon. While this event is billions of years away, it highlights the ongoing, evolving relationship between Earth and the moon, and the gradual changes in the Earth-Moon system that will shape the planet's future. Furthermore, the study of tides is crucial for understanding the potential for life beyond Earth. Moons like Europa and Enceladus, orbiting Jupiter and Saturn, are thought to harbour subsurface oceans, kept warm by tidal heating generated by gravitational interactions with their parent planets. These moons, shaped by tidal forces, may hold the key to understanding life in extreme environments, and tidal research will continue to be essential in the search for extraterrestrial life. Just as the moon's tidal forces have shaped Earth's environment and ecosystems, they may play a role in creating habitable conditions on other worlds. As we continue to explore space, the lessons learned from tidal forces on Earth will help us better understand the dynamics of other planetary systems. Tidal forces shape the movement of celestial bodies, from moons to planets to stars, and by studying these forces we gain insights into the evolution of the universe itself. The study of tidal interactions also holds potential for uncovering new information about the formation and behaviour of celestial bodies, including the distant moons and planets we have yet to explore. Tides, then, are not just a curiosity of Earth's oceans, but a key to understanding the larger workings of the universe. They remind us that even the smallest, most rhythmic forces are interconnected with the vast cosmic systems that govern the natural world. The study of tides offers us a window into the deeper patterns that shape our planet, and through that understanding we can gain a greater appreciation of our place in the cosmos. Whether it's the gentle pull of the moon on Earth's oceans, the shifting tides of distant moons, or the grand cosmic cycles that govern the universe, tides teach us that all natural forces are interconnected, working together in a constant, harmonious dance. As we continue to explore the moon's enduring influence, we are reminded of the vast complexity of the universe and the enduring rhythms that connect all things.